Hello, everyone. Thank you very much for joining today. It is my great pleasure to present to you the future of drones, or how the future of integrated drones and sustainable drones can look like. My name is Mirko Kovac. I'm professor at EPFL, which is the Swiss Federal Institute of Technology in Lausanne, in Switzerland, and also the EMPA, which is a material science institute in Switzerland as well, close to Zurich. So we have a joint group between the two working on sustainability robotics. So what really excites me about that is the idea that drones and robots in general are integrated into the natural environment, into our lives, in a life-supportive and positive manner. So the question is, how can we design such robots? How can they be integrated? How can they become natural inhabitants of the natural world? And how can we design them, build them, develop them to be such sustainable integrated agents? So I'll now share the screen and give you a quick overview of some of our work in that direction. And afterwards, we have time for questions. I'll take the chat here and answer some questions that have come through. Thank you again for your attention, and your ideas, comments, questions are very welcome. So the future of drones, I believe, is a lot about biology and about the integration with biology. So what we see here is not a drone, it's a natural system. So it's an insect, a flying insect. And there's a lot that we can learn from them. For example, we can learn how they fly, how they're built, and how they operate in those unknown, constrained outdoor environments. And there's a few things that they do very well. For example, they combine sensing, control, and navigation. Sensing from their antennas, their structures, the sensory system, from the eyes, from the other sensors that they have. They then control it with neural networks. They navigate using various modalities. And then they integrate this with aerodynamics and very complex flapping wing aerodynamics, in fact, which they master very well. They also use various materials, soft structures, and actuators and muscles to allow them to fly, to move, to engage with the environment. Now, the important thing here, I think, is that they co-evolve all of this. So they don't start with an empty shell, a body with motors and actuators, and then add the control on it. They co-involve the learning, the control, the sensory system, the muscle system, and the structures and materials all together as they grow, as they interact with the environment. And I think this is something that is often missing in the way how robots are built. Robots often start in simulation, then get tested in a laboratory, and then get translated outdoors in a very rather linear manner. But here we have very much a circular development philosophy, if you can call it like that, that allows these insects to move very efficiently outside. But I think we can learn a lot and also develop robots in a similar manner. If you take an example here, if you have an example of a robot that attaches to the surface, so that wants to perch on the surface and land on the surface, like the perching eagle, for example, we can build that into a robot using a control system and sensor system, allowing it to pitch up and do a deep stall maneuver to attach to the surface. So this requires control, sensing, planning, deep stall maneuvers, flight control, and so on to do so. However, when we get very small in size, such as the RoboBee, as you see here, which is less than a gram in mass, we can benefit from other methods. And in fact, we can benefit from the mechanical intelligence methods that many insects use. So the bumblebees or the flies, for example, they use their antennas and the legs to adjust and attach to the surface. So it's a mechanically mediated transition where the mechanical body and the morphology is used to enable this transition, making it a mechanically intelligent way of doing so. So we can think of this as a spectrum from mechanical intelligence to digital intelligence. And I believe that if you want to create lifelike vehicles, lifelike robots, we need to integrate and benefit from both to create a true lifelike intelligence. And this is exactly what we have been working on for now, I think about 15 years in the laboratory at EMPA and EPFL, but also previously at Imperial College London in the aerial robotics lab that I was setting up and leading before that. So the idea is to create a robotic army knife, so a Swiss army knife that is the robotic capability that can then collect data and monitor climate, water, forests, smart cities, infrastructure, and also interact and modify those environments. For example, doing repair tasks or other like planting, smart agriculture tasks, forest health, forest maintenance tasks to really protect and maintain those environments. Now, if you want to do that, we need to be able to deal with various environments. And one of those environments, of course, is air. Now, air is a very natural environment for aerial robots, but it is very complex because of the turbodynamic, because of the fluid mechanics, turbulence, and so on. And so here's an example of how we think about sustainability robotics in an aerial domain. So we can have a flying vehicle that then launches those small sensory vehicles, sensory agents, like micro robots that are being deployed in the natural environment. Those agents then sense the environment, sense the biodiversity, sense the physical parameters like temperature, light irrigation, and so on, and can, like this, provide the intelligence needed to get insights onto the climate and onto the biodiversity in those environments. Eventually, those vehicles can be not just be manufactured and then be used, but they can also biodegrade, so they can die, so they can have a targeted death in the environment, then integrate back into the material of the ecosystem, so being compostable or biodegradable, and then eventually even regrowing. So can they heal? Can they be reproducing in a way that they would regrow and then be used again? So this is the larger vision for this approach, which we call the transient robotic life cycle, where the robots is like an animal integrated into the natural life cycle. So here's a robot that does part of that, which is to fly, then detect a spot where it wants to place a sensor, and then can launch a sensor, model the trajectory, and place it with a precision of a few centimeters on a few meters distance. So this allows it to place those sensors quite effectively at height, where usually people would need to climb up and place the sensor manually, which is of course expensive, it's risky, and it's time consuming, and because of that, a lot of the environment is undersampled, so not enough data is there. So, but by using flying vehicles like here in the forest that would then fly and then place those sensors, we can collect data that is unprecedented, data that is novel and abundant, allowing us to measure the biodiversity and measure various environmental parameters. Which environmental parameters will we want to measure? Of course, it can be various physical or biological parameters. Maybe it could even sample the surface of the tree. But the first modality we went for in this example is to measure the bioacoustics. So this means it has a microphone, then collects environmental data, and this data is then analyzed using machine learning algorithms to then identify which bird species are there and how many of which species are there. So there's the two parameters called abundance and species richness, and we can measure that across the layers, so across the height or in the canopy here in the trees. Basically, this allows us then to study and to quantify where the birds are and how many there are. This is a really important metric in order to then study how climate change influences the bird populations, how noise pollution influences them, how chemical pollution or human activity influences them. And by knowing that, we can better protect those environments. So the robot becomes a tool in order that allows humans to collect data quickly, get insights, and then design the policies to really protect those environments. Now, of course, the holy grail is to integrate them fully, and therefore we need the biodegradation and regrowth elements of this. So we work on that for quite a few years, but one example that I would like to show today is the manufacturing method which allows us to create those biohybrid cryogel composites. So these are composites that, for example, have gelatin solutions or starch solutions linked with, mixed with microfibrillated cellulose, so which is a wood-based suspension, and then can be poured into molds, then be freeze-dried, which allows us then to create those kind of porous structures, which you see here in the middle. These structures can have various performance levels. So depending on how we manufacture them, they can be very rigid, or they can even be soft, and like this have different performance levels, while also having designed biodegradability properties. So we can design both how it performs and how it biodegrades. This is the basis for really tuning the system and the process to create those transient robot life cycles. Now, eventually, in the near future, this is about having static sensors, static robots that just sense certain parameters in the environment. But in the mid to long term, they can become agents that are robotic by themselves, that move through the environment, like using environmental vectors such as rivers or animals, but also move by themselves using humidity-triggered actuation, for example, or other methods that are fully materially enabled without the need for motors or batteries. So the material science itself informing or enabling the vehicle, the structures to move or adapt, and like this become intelligent robots in those environments. So a lot of open questions to achieve that, but it's a really promising field that is developing now internationally. The second environment, which is also very important for us, is water. And in the water, we want to measure, for example, temperature or acidity, which is important for coral reef protection, but also the biodiversity. So knowing which animals are there, what microbes are there, or microorganisms. Are there any invasive species, such as different kind of species that don't belong to the ecosystem? Or is there microplastic pollution or chemical pollution in those environments? Can we collect environmental DNA to measure and quantify what is happening inside of the water? So this is really the basis for water health, and robotics can really be a very important tool to study water health. Now, this is something that we work on for many years now, for about 15 years. We wrote a book, which you see here, and here's some papers that are related to that. And the overall vision you see in this top picture, building completely soft metamorphic robots that can fly in air, but then transition into the water, move underwater, and transition back to flight, or transition into sailing abilities. So to sail on the water and like this saving energy for long duration sampling of the environment. Okay, so let me give you 2-3 examples here. Number one is this idea to have this impulsive exit from the water. And this we built in this system where we use calcium carbide that can react with water, creating acetylene gas. This acetylene gas mixed with air can then be ignited and can eject the water from the body of the robot. By doing so, it can boost the vehicle from underwater into the air quite efficiently, quite effectively, I would say, with a very high thrust boost. A bit like a water rocket that has a combustion to boost the water out. So you have the spray, then you have the gas jet that follows, and then it has a glide phase of about 23 meters by using only 0.3 grams of calcium carbide. So it's a quite powerful combustion that is happening. Similarly, in collaborative work here with Harvard University, who work on this RoboBee, so that's the size of a real bee, but it's a robotic vehicle. We looked into ways how to have this transition happening effectively. And here it uses an electrode that is splitting the water into hydrogen and oxygen, which then can be ignited and again gives like this a bubble that is burst out of the vehicle, allowing it to jump out of the water. Again, impulsive transition from underwater to air using combustion-based methods, which are very high power. And like this can be used for that quite well. Now, once in air, it can keep on flying, or it can land on the surface and then do sailing. And to study this transformation from flight to sailing, as you see here, we built this SailMAF vehicle, so sailing micro-air vehicles. The idea is that it lands on water, reconfigures into sailing, property, a sailing configuration, and then uses a custom flight controller to sail on the water surface autonomously. The vehicle itself is built from scratch, so the design as well as the manufacturing of the wings, of the structures, the fluid mechanics, even novel sensors that needed to be integrated, and the flight controller are developed specifically for this vehicle. It then enables it to do motion on the water surface using the propellers or using sailing, then transitioning into hydroplaning and ground-assisted takeoff. A lot of this actually is not known, like a lot about the fluid mechanics is not known at this scale, so we had to do a lot of fluid mechanics studies as well to understand and optimize the vehicle. But this vehicle, I think, is a good example of how we can think about sustainability robotics, where we go all the way from concept to systems to data-based insights. And here the concept is aerial aquatic transitions, reconfiguration for sailing. We then build the robot, optimize it, test it in the laboratory, test it outdoors, and then test it outdoors and collect here again environmental data like the soundscape data. This then gives us insights onto the bird populations in summer and winter in disturbed and protected environments, showing that really there is a quantified measurement of increased bird species populations and diversity in the protected environments across seasons. So this is a valuable insight that really helps us to protect and to make accordingly the policies to protect those environments. Good. The third environment is, of course, Earth. And the question is, how can we do Earth shaping? Can we use Earth to manufacture structures? Now, this is something we are also working on for about 13 years now. And we built various robots with the idea that they would collectively 3D print structures from flight. So they would fly, maybe collect environmental material, and then print and 3D print those shelters, support infrastructure, habitats in inaccessible environments here on Mars, but also maybe on the Moon, and also in inaccessible mountain environments or natural environments, or anywhere at height where it is dangerous and difficult for humans to access. Of course, naturally, we start with the biological review of how biology builds, and there's a few key methods that biology uses that can be really very useful for robots too. For example, using templates, which is using local initial conditions for the manufacturing process, and then robotic rules or instincts that allow it to scale from those initial conditions. Equally, decentralized controllers with emergent properties based on the material or mechanical design of the robots, or local interactions with the environment or with the agents themselves can allow for emergent properties in the construction process. So these are directions that the construction industry is not using today, human construction, but which really could be very beneficial for the next generation of construction, which will be robotic. So the robot we built, here an example, is a flying vehicle that can stabilize an extrusion head and deposit material from flight. Here it does that with a precision of a few millimeters and can extrude high-performance cement material to make layers, and like this make and build larger three-dimensional structures. So this is aerial additive manufacturing, or aerial 3D printing, as we also call it. It is autonomous. It uses its own controller, its own design of the mechanics, its own architecture of building, and its own material that all needs to be co-evolved in order to achieve that. So if you use a different material, such as here polyurethane foam, we can do so and then build structures maybe even at larger scale, because the material expands, and like this can give layer heights that are higher. The problem is, however, that the material expansion is very difficult to predict. So it could do so, expand, but then we need to adjust the next layer of the printing process accordingly to then have the next layer in the process. So this is what we call here the closed loop aerial additive manufacturing, where the scan drone, so the scanning vehicle, collects the three-dimensional information and extracts the ridge line and adjusts the printing step to such that it can scalably build different layers and build larger structures. So this is really the goal is to have the monitoring of the process, the quality control and adaptation of the process in the loop. We also went to the Architectural Biennale in Venice in 2023, where we showcased that with the question of how such a process could really affect architecture. So how can architects now build differently, assuming the capability that we have swarms of those flying vehicles that collectively can build larger structures? So it's a new method which allows for new design freedoms as well. And I think this question is a very interesting intersection of architecture and robotics. Now, besides this continuous aerial additive manufacturing, there are also tensile, like web structure manufacturing or discrete assembly of structures. And we work on those as well, but for time reasons, don't include them here. What I would like to mention, though, is the autonomy, whereby most starts with a just simple pre-programmed trajectory, then the aerial physical interaction, or maybe online flight planning and manufacturing task planning. So this is a lot of pre-programmed behaviors. But at level 4 and 5, we get into closed loop or multi-agent scanning in the loop manufacturing, where it scans and then adapts the process, or even does a full structural assessment and design in the loop. So can robots do the whole design process based on what they have built already? So most has actually in this field is about level 1 and 2, and maybe 3, and we are now starting with this level 4 with this scanning in the loop process, with the goal to then go to level 5 of fully autonomous design and structural assessment in the loop. So the fourth element is fire. And fire, of course, is challenging and has inspired us to create a robot that can fly inside of very hot environments or in and around fire. The system here is built using novel type of materials called the polyamide, fiber-reinforced polyamide aerogel, which is very heat resilient, and then in combination with the cooling system and the different mechanical design of the robot can allow the vehicle to fly in very hot environments, here above 200 degrees, where it can then monitor forest fires, building fires, or hot industrial environments. So this is something that we have been working for quite a few years and have now also are doing a spin-off on that called the Fire Drone, which has also received quite a lot of support and industrial traction. And it's really an example of how novel drones that have co-evolved materials, structures, and applications can really bring value, being lifelike systems for inspection of challenging environments. And this really brings us to the fifth element. Now, what is the fifth element? The fifth element is the innovation, it's the creativity, it's the free mind that can manifest these different ideas, various robotic solutions, AI solutions to the world. But it's also an element that connects people, that aligns ideas, that aligns the visions of different people alongside the applications and the value chain in society. So I'd like to mention two aspects of that. The first one is the philosophy of development of those vehicles. And here we wrote a paper a few years ago on this co-development of material science, robotic structures, and the chemistry, the computer science, and the materials to create those lifelike robots. This co-development method we call physical AI. The second one aspect of that is the bio-inspiration. So in 2014, I wrote this paper on how to do biological inspiration, call it the bio-inspired robot design paradigm, where we can take inspiration from the biology, then abstract the principle, then build it into the environment, into the robot using the best of our engineering knowledge. So I think the combination of this method of design with the co-evolution of disciplines, I think is the key to create lifelike robots. The second aspect that I would like to mention is the testing infrastructure. So there are a lot of indoor test environments, flight arenas, and so on around the world, and there are a lot of outdoor environments as well. But there really is a gap between them of environments that are protected, instrumented, but are representing outdoor environments. And this gap we are now filling by developing the drone hub. The drone hub is a new type of test infrastructure located at EMPA in Zurich, next to Zurich, where we can test novel types of robots in a representative, highly visible, and integrated way with humans and other technologies in the building sector. It has three innovation elements. One is the aerial additive manufacturing facade or infrastructure, where you can do repair, manufacturing tasks with the robot. The second one being the biosphere, where you can test the biodegradation, sensor placement, biodiversity monitoring. And the third is the facade and integration with the facade, where the facade can become adaptive and integrate with the robot motion, the sensing, and interaction with the building itself. So all of this is a showcase, and it's an opportunity to study how together as a society we can demonstrate those systems. And the drone hub is open for collaboration. It is built, so that's a photograph of it in the background that you see. And we have opened it last year, so it is open for ideas on doing that impact together. This is all part of the Global Competence Center for Sustainability Robotics, which we have launched, where we combine sustainability science and robotics science on the research development and proof of concept level to create global visibility, startups, insights, and new technologies, really forging the path forward for a new impact of robots being the key elements of a sustainable future. With this, I would like to thank the funders, previous members of the lab members that are working on this very hard, and also you for your attention. Thank you very much. Good, so I stop sharing. Let me see, there's some questions here. So just feel free to add your questions. I'll try to answer them as they come in. Question number one is, how energy efficient is using drone-based additive construction? Are there any comparatives to traditional methods, even if this were to be done at scale? Oh, that's a very good question. We asked that as well to ourselves, and actually we are writing a publication on that, where we study and quantify the energy consumption of the process and compare to existing methods that are being done today with humans and so on. I don't have the coherent, kind of quantified answer at this point, but I can say that there are a few benefits of this process. One is that the logistics is easier. You don't need to bring a big crane, which is also has a lot of CO2 footprint and energy footprint. And then smaller agents are easier, more agile, and can be adapted based on what needs to be built. So there's certainly a benefit of that, especially in inaccessible environments. So everything at height, everything in mountains, everything in space, for example, really can benefit from multi-agent systems that are mobile, smaller, and have the swarm control. So this is a qualitative answer, but the quantitative answer we are still working on. Good. Second question is, which undergraduate degree is best to study robotics? Should it be electrical or mechanical or chemical engineering or material science, or does a degree in robotics cover the required fundamentals? I think that's a very good question, and I think it can be any of those. Eventually, and I believe this is important, is the multidisciplinary integration, so that as a student, as a researcher, one is able to understand other disciplines, be interested in them, and integrate them within the same philosophy and framework of design and development. I think this is very important, but it's also very challenging, because at the same time you need a specialization in something, while also you need the breadth of integrating other disciplines. So it's really both together, and therefore it's possible to come and enter into this paradigm of physical AI from different directions. So there's there can be many ways for that. What I would say is that it's the most helpful is to just feel where the interest naturally, the intrinsic motivation and intrinsic interest resonates with oneself, and then enter from there. And from any of those disciplines mentioned, I think the path can be towards this living, lifelike robots. Good. The third question, for the 3D printing aspect of the drone, how much filament 3D print material would you store in each drone? Yeah, this is depends on the size of the drone. It can carry a few kilograms to a few hundred kilograms. It's a question of scale of the drone. The framework we developed is agnostic, is independent of the payload of the drone. So it can be as much as you need. Eventually, a drone can be a helicopter size as well. I would say, however, that the sweet spot for most of these construction and repair use cases are a few kilograms. So if one drone can build a few kilograms of material as it goes and flies there, it can then come back and refill and exchange the motion with another drone. The problem is not just how much it can carry, it's also the battery it has. So it would naturally need to come back and fly again. So it's a coupling of the battery flight time and battery capacity, material capacity, and the use case of what it needs to do, and how many of each drone there are. So all of this together can give an optimum of how many are needed for what and how much they should carry. In the publication I mentioned, we have studied that and done different scale-up methods to answer that question. Okay, as an experienced drone pilot, I worry about the future filled with UAVs and their effect on birds and other flying creatures. How do you think drones would impact the living flying creatures? This is something that we have seen as well. Of course, robots and drones can also influence the birds negatively, but I think it needs a very responsible use of those, and it needs to be in accordance with the protection of the animals. So we cannot just deploy them blindly in the natural world. Our approach has been to use perching or intermittent locomotion, as we call it. So flying and then resting and then flying again, and then measuring different things as it is also resting on the tree. Now, this resting is non-invasive or minimally invasive. It is silent. It can just perch there and observe the environment, measure biodiversity in different ways. So while doing that, it is much less invasive and influences the bird populations less. So I think the key is somewhere around these intermittent behaviors or that make it minimally invasive, and also being smaller in size, so being less invasive, and for sure, or in many ways, less invasive than any comparative human activity where a human will go somewhere and take the same measurement. So another question, skimming through. So what is really possible in drone using AI? So AI, I mean, AI, of course, can mean many things, but I would break it down into AI of the environmental perception. So drone has a payload, like a camera, and then AI is used to do something with the camera image. There, of course, can be all possible types of environmental classification, crack detection, damage detection. An example of that would be ash tree dieback detection. So ash trees, they lose their leaves due to a disease that affects, I think, about 50% of trees, ash trees in the UK, or even more. I think 50 to 90, I've heard, of ash trees in the UK have this one disease, and they lose the leaves, and this is really very bad for them. So how can we use drones to monitor them? And so we wrote a paper using a YOLO algorithm, which then takes camera data from the drone and can classify the leaf density loss on those trees. We also there used, for example, simulation environments and different game engines to simulate different trees and then add this to the training data set to train those algorithms to detect the leaf loss. So this is an example of payload and then data and then AI on the data. There's also a separate field of using AI on the control system, so the flight behavior of the drone. And this is a big field using neural networks. And there's a variety of options of tuning the gains or have model predictive controllers that have AI integrated at different levels. And so it's also a big field that is, for example, helping in racing drones or highly agile drones and so on to be more high performance. Our example on this would be to have adaptive depth neural networks. So neural networks that are not rigid in structure, but where the depth of the structure changes. And then can, depending on the environment, so turbulence or no turbulence, can change the depth of the neural network and like this be more performant, but use more energy, or be less performant and use less energy with a simpler neural network and change between the states. So that could be a second example. So from your perspective, what adaptations or innovations are needed to make these technologies truly effective in such environments in the global south? I think that's a very important aspect, that the technologies can be very expensive, right? Drones of some that I showed can cost many tens of thousands of dollars, and like this become inaccessible for many people that cannot purchase them. And so I think a lot is about making them more accessible, the technology more accessible, which is the open source mentality to the code, to the designs, to the manufacturing methods, also using environmental materials that are easily accessible. And I think cellulose or wood materials are a good example of that, that is really abundant across the world. Last but not least, I would say that the innovation can also go in the direction to make simpler systems that are more accessible and have local community hubs where manufacturing, 3D printing, interaction, engagement with those technologies can be encouraged with the local communities. So I think a lot is around this philosophy of education, learning about it, exposure, bringing the systems to the local communities, but then also using materials, manufacturing methods, and designs that are accessible and can like this democratize the robotic solutions for various applications in different communities. Another one question here is, do you see a future where drones don't just mimic animals, but actively collaborate with them in the wild for mutual benefit? I really like that question, because how could they collaborate, right? I mean, of course, they should not negatively affect the environment or the animals, but there might be a symbiotic relationship. And how can such a relationship look like? I think it's an open question. I don't have the absolute answer on this, but it's something that really will pose itself. An example of that is a penguin that was developed like a robotic penguin and was used to study penguin populations by mingling together with the penguins. And then insights on those penguin behaviors and so on were extracted from the recordings, from the data collected from this robotic penguin. This is an example. Another example are the measurements we did in the lake with the sail mouth. So with this sail mouth, we were able to silently sail through the lake and come closer to some animals and detect some animals that manually were not detectable, or that the engineers and the ecologists told us they were not able to sample. So by using the robot and making it minimally invasive, we were able to come closer to the animals, like this collect data that was not available beforehand. And I think that's the sweet spot as well, of having minimal invasive, hybrid, mixed colonies, mixed environments where robots, the environments, and animals, and also humans can live in a more synergetic manner that is symbiotic even potentially and does not negatively influence each other. So another question here, what is the environment you dream of sending a drone into, but current tech makes impossible? A wonderful environment example for that would be space. And of course, space is an example of an inaccessible or hard to access environment. But I think there's a lot of potential on the moon, on Mars, to have robots and agents do sampling, manufacturing, interaction, exploration, and so on. Where exactly you don't necessarily want to send a lot of humans to do the same tasks. So robots can be very powerful tools for that. I think in order to do that, we need different testing environments, and we need also new approaches, design approaches to do so. The test environments, the drone hub is an example of that, where it can also simulate different types of inaccessible environments, potentially also space environments. We have other flight arenas where also we're planning to do an integration to really represent various environments and then get them closer to those environments. Another one, of course, is mining or underground, deep underground. So the mining industry really can benefit a lot from automation, but also from new types of robots to do sampling, optimization of the mining process, making the mining process less invasive, more environmentally friendly, more sustainable, maybe doing even some of the actions underground, which are currently not possible. And like this also protect the humans not to have them so deep underground. So I think that's a second environment, which is very hard to access, very hard environment, but where robotics can really bring a lot of value. So another question was, how do you manage the challenge of power consumption by inspired drones? Are we close to creating self-charging, fully autonomous drones that could operate infinitely in remote areas? Yes, the full lifelike capacity of energy harvesting, material repair, like self-healing, maybe even reproduction between robots, between drones, is of course a bit away from our current state, right? So it's really challenging to do so. But some of the work that the community is working on starts to look into energy harvesting, so solar cells, but also as an example of the sailmath, using wind vector, so wind to make the motion of the robot, to make it move at low energetic cost. The biodegradation is a direction into the life cycle integration of healing and maybe regrowing. So I think the community is making some advance into that, but really we are at the beginning of the whole field. So there's a lot of white space, a lot of open space, a lot of potential for innovation, for people to come in with their ideas and contribute and develop and showcase how this could be done in a positive manner. So there's like a lot of questions. I'm just kind of scanning through. Yeah, one is a question, what are risks associated when doing drone-based monitoring and sampling? Of course, there are always risks, um, technical risks, operational risks, financial risks. When doing a mission outdoors, from our side, what we have seen is the complexity of the operations. So there's unpredictable elements in the operation, in the field, that make it very difficult to build something and test it quickly. For example, there might be currents in the water that bring the drone away. There might be small waves. There might be interaction of wave and current and the sensors and the light and the heat or the humidity or that influences certain electronics. And these are things that are very difficult to test in a laboratory. So it's very difficult to predict exactly what can happen. Um, one example was in the desert. Once we were testing a drone in the desert, and the temperature was very high, above 40 degrees. And it was something about the sun irrigation on one of the sensors, one of the electronics boards, power distribution boards, was such that suddenly it didn't work, and then again it worked. So it was intermittently working and not. But we worked on this drone for several months in advance of that, but we couldn't test this, or we didn't think that this would influence it that much. So eventually we had a mitigation of that for the actual demo and test that we did, which worked fine. But really one of the examples where the unpredictability of the environment, of the weather, of the sand coming into the motor, or things like that, can really greatly impact the mission success. So when doing field testing, it's extremely important to do this iteratively, to test a lot, go out, really test it, test subcomponents, integrate them, and also work with people who are field savvy, who have done some testing outside, who know about the weather, who know about the environment. So it's really a challenge. It's a lot of unpredictable factors that come into play. What's the most fascinating biological phenomena or animal behavior you've encountered that was inspired by one of your drone designs? I mean, I'm an enthusiast of animals in that way, and one example is the spider. So the spider is able to weave structures. So the spider 3D prints a filament from its own body. So it eats something and then 3D transforms this into filament material, then 3D prints that from its body and can suspend itself with it, then builds this to unknown anchor points to the tree or the environment, and then uses local rules based on what it has built to build integral structures that are very structurally strong and that are a sensing material. So it then sits in the middle of the net and uses the net as a sensor to detect when prey comes into the net, but also to use it as an extended phenotype, as they call it, to measure environmental conditions of various types. This all without knowing anything about the environment, by tuning its own 3D printing process that it does with its body, and using local rules of manufacturing, using a minimalist vision system. So they don't see very well. They use minimalist vision and tactile information to do so. So it's an engineering masterpiece to do that. So with robotics, we're really very far off this. But it's an example of how animals combine materials, behaviors, structures, the intelligence of their body, tactile information, visual information, environmental information, local emerging behaviors to construct and interact. And not just that, they also, reproduce, collect food, and so on. So really, I think it's very humbling as an engineer to know that biology, what all biology does. And I think there's still a lot of open innovation potential in this direction to create those types of robots. Okay, and last questions, and then I think we can slowly wrap up. We're exploring the use of drone-based LiDAR and multispectral imaging for biomass estimation, canopy health monitoring, and carbon stock verification in multi-species biodiverse plantations. So, does it have potential? How to use it for sustainability? And I think it can help of course, in the data collection. In the data collection, biodiversity, but also, exactly as mentioned, the biomass, for example. So measuring trees, just simple parameters like the tree trunk diameter of a tree, to estimate the biomass can be extremely valuable. Another example is 3D mapping of environments, for example, of waste or of biological material in the environment. This already can give quite a lot of valuable insights onto the carbon cycles and so on. Now, besides that, this is just like a vision-based simple sensors that can do a lot of value already, like topology mapping and so on. Agriculture, like just the growth rates of different plants, the health, like the water need of the plants, irrigation needs. And so a lot can be done just with the flying robot that takes visual data or multispectral data from flight. The next generation then starts with the interaction with the environment. So, for example, sampling the leaves of a farm field to identify some invasive species or pests of the farm field. This can be very helpful to do so more quickly or more regularly compared to humans having to walk through the farm field to get the similar information. So interaction-based sensing by sampling, taking some readings, taking a sample, looking at the DNA footprint of those samples. And this can be very, very valuable as well. And then the third generation or the third wave, which will come, I think, is to take all of this information and then do tasks. So precision spraying, precision interaction, surgical interaction with the environment, with chemicals, with biological material, with maybe actual animals or insects and so on, that can help it to really restore or influence the environment. So I think this, from non-contact-based sensing to contact-based sensing to contact-based physical interaction and management, active management using robots. So these, I think, are the three waves. Again, we're in the beginning, and I think there's a lot of open questions. So looking forward to see how the field develops and how all of you can join us and contribute to this discussion and to this whole field. So any questions, anything, ideas, collaboration ideas, or anything that comes up, please don't hesitate to be in touch. You'll find us on the websites and also here in the comments. Thank you very much.